Okay, hi. So this is the second part of the introduction for chromatography. So this slide is showing you the output of any chromatography instrumentation. Okay, it is the chromatogram. Okay, so it is a plot of signal or response versus retention time. Why do I put this signal or response over here? Because it is depending on your detector. Okay, if you are using HPLC with UV, the Y signal, the plot of signal is milliampere unit. Okay, and if you are using GC with FID, the signal will be millivolt. So it is depending on the detector, and the x-axis is always time. Okay, so if you want the x-axis to be mass to charge ratio such as in MS, you can do that, but it's different diagram. It is not called chromatogram, rather it is used to call mass spectrum. Okay, so in a chromatogram, what you can see is the peaks. Okay, when you do chromatography, all you want to see are peaks. Trust me, once you see peaks, your life is easier when you're doing analysis. Okay, that means that the analyte is finally eluted out from the column, reaching the detector. So this is a time 0. Okay, so this is time 20, for example. So in time 0 means that you are just started to inject your sample, either in GC or HPLC or CE. So and then once you inject, you will see like a small peak over here. We call it as void volume, or sometimes we call it as the solvent peak. Why it is called solvent peak? Because in the system, only solvent is not absorbed on the stationary phase. It will just go towards the detector and be detected over here. So even though it's small, it shows and tell you a lot of things, such as it tells you how well the column can retain analytes and how well the column will resolve peaks. So this little fella over here is very important in any chromatography. Okay, so it is denoted as T null. And then we have the first peak, and we denote it as the retention time for first peak. And then this is the retention time for second peak. We have peak height. Here is peak height. And then below this peak, we can calculate the area. So how to calculate the area is based on the Gaussian peak system. And usually this is integrated automatically in your chromatography instrument. And then we have the peak width, the kelebaran peak, okay, at the base and at the half of the peak. There is a reason why we have two. Usually we use the peak width over here when your peak is slim, tall, and pointy. But if you have a very broad peak, sometimes this can help you to calculate the efficiency. Do you still remember what is the efficiency label? It's N. Okay, so next to the next slide. So information from a chromatogram, you can get a lot of number of peaks correlating with number of components. Okay, so this is qualitative lah, Quali. So, and the second one is you can know how much or what is the concentration of the component just by looking at the peak area or peak height. How do you get this? This is when you integrate the peak first, okay, using the software. And then if you have a standard solution, you can identify what are they. So the plate theory can also be used for peaks. Okay, remember before this, I introduce to you guys what is the meaning of theoretical plate, because it's the theory. It is actually only theory. It does not exist per se, but it comes from the, just like the fractional distillation, remember? Okay, so means that when the gas comes out, the plate will be like this. Okay, it will be up, and then it go down again. So because of the repetitive up and down over here, we can calculate how much is the plate. So the higher the plate, okay, the higher the plate, okay, the higher the efficiency, the N. So in this slide, it shows that how this peak is related to Gaussian. Okay, the one that you learn in your statistic, right? So everything here you can calculate and know the area. It is correlating to your concentration or amount. So this is the Gaussian peak shape. This is the equation, everything. I don't want to go into detail because I believe you already know all about this in statistic already, and how standard deviation is very significant in Gaussian peak. Okay, so now we go into the definition of chromatography. Several jargons that you have to understand, and I hope you still remember from your previous class with Dr. Azli. Retention time is the time elapsed between the injection of sample and the first peak maximum that you see. Okay, mobile phase hold-up time is the dead volume or void volume, and then you have the adjusted retention time when you minus the retention time with the void volume. And then you have the retention factor, whereby it measures how long a sample is retained with respect to that volume. Okay, the K is usually between 2 to 11. You want to be in the middle, you don't want to be very minimum or very maximum, because it shows that how long or how fast the sample is retained. And then you have the efficiency, the N. You want high N. And then this is the effective theoretical plates.